All right, so this is for Computer Science AS Level 9618 1.3, which is about compression, lossless compression, lossy compression, and run length encoding. So let's take a look at our learning targets for today. So candidates should be able to show understanding of the need for and examples of the use of compression, show understanding of lossy and lossless compression, and justify the use of a method in a given situation, show understanding of how a text file, a bitmap image, a vector graphic, and sound file can be compressed, include the use of run length encoding, which is abbreviated as RLE. So all that we'll dive in today. And of course, if you're my students, we'll be taking these notes at home and doing all the activities and homework inside class. So let's jump in. So file compression. Now, sometimes a file needs to be compressed, and this means reducing the size. When we're talking about compressing a file, we're reducing the size. Now, reducing the size can save storage space on our own device. It can also reduce the amount of time needed to transmit the data or stream the data from one device to another. MP3 files, those are compressed audio files, and something that everybody's very familiar with. If they were not compressed, they would be much larger and you wouldn't be able to fit as many songs on an MP3 CD. MP4 videos, those are compressed videos, and those are simply multimedia files. And there's two types of compression that are commonly used. The first one is lossless, and the second one is lossy. So let's go ahead and continue and take a look at some lossy compression. So here we have two sound files, and we just got done talking about MP3s versus the original format it's in. The original format that it's in is a WAV file, which is on the right-hand side right over here. On the left-hand side, it's an MP3 file. And you can see the size difference is huge. In the original file, we have 45.8 megabytes, so almost 50 megabytes. Here, right over 6. So for this Volbeat song, Lola Montez, we can see that when we use an MP3, we have it's compressed way down. It doesn't take nearly as much storage space as possible, and the MP3 sounds pretty close to the actual file, and we'll talk more about that later. So lossless compression, let's talk about that. Now, all data from the original uncompressed file can be recreated once it's uncompressed. This is important for files that cannot lose any data. So we're not losing any data here. Think of a Word document. You cannot lose any characters from the Word document. Imagine you're typing a term paper and you just lose characters from your term paper. It's going to look like a set of random letters. What about a spreadsheet showing savings or financial details? You wouldn't want to lose those either. Now, there is a form of lossless compression that's called run length encoding, and it is lossless compression. It's one form, and you can actually take large characters and shrink them down by saving space. So let's jump in and take a look at that and combining it with compressing a text file. So here we have some tables, which we'll get to at the bottom. So run length encoding, also known as RLE, is just abbreviated, is a lossless compression that reduces a file based on identical data. Now, it's only effective when there is a long run of repeated units or bits. If you don't have a long run of repeated units or bits, you may not want to use run length encoding. So let's take a look at the following string, and all I have here are some random letters, okay? I have a series of A's, B's, C's, and D's. That's because I have some repeating bits or units here. So we can use lossless compression to compress this string. The compression of the file would look something like this. And down here, I have 05. What is that referring to? That's referring to 597. 97 on the ASCII code table are my lowercase a's. 0498. I have 4 lowercase b's. 98 is the ASCII code for the lowercase b. I have 2 99s, which is lowercase c. And then I have 5 100s, which should be D's, not A's. That is a typo on my part. These should be the letter D. All right, so let's keep talking about it. So this is the string that we had. And for this example, we'll say each character takes 1 byte of data. Now, this means the file will be 16 bytes long. After running the compression, here's what we'd wind up with. So here's our table again. So let's say that each number takes up 1 byte. We have 8 numbers, which means 8 bytes. Lossless compression has been able to cut the file size in half and we didn't lose any of the data. We still have all the A's, the B's, the C's, and we still have all the D's. This is a typo on my part there. Now, in the previous slide, we said it's useful with repeating bits, but there's something that lossless compression can use to cope with non-repeating bits, and this is called a flag. Now, if you're in 9608 computer science, they did not cover this next part that we're about to talk about. So let's take a longer string here, a lot of A's, a B's, followed by CD, 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 and then a bunch of E's. For this example, we'll say each character again takes 1 byte. This means the file will be 32 bytes long. After running the compression, here's what we wind up with. We have 0897, we have 1098, then we have 199, 1 100, 199, 1 100, 199, 1 100, and then we have 8 101, which corresponds to lowercase e's on the ASCII code table. So it's not very beneficial to use run length encoding because my CD, CD, CD doesn't repeat. But there is something built in that we can use for non-repeating bits. So now this right here, without having our flag in, which we'll talk about, reduces the file size to 18 bytes. But lossless compression incorporates a flag for reducing the file size even more. Now, the flag in this case will be 255. They're going to give you a flag. Now, the flag shows there are repeating values that deal with the next 2 bytes. If there is no flag, the very next byte is taken with the preceding 0, 1. So here's what it would look like now. Let's start with the 8 lowercase a's. I have 0897. The 08 refers to how many characters I have. The next 97 here shows me the ASCII code character, which is lowercase a. 255 says, okay, we have some repeating values here. And it says right here, the flags show there are repeating values that deal with the next 2 bytes. So I'm looking at these next 2 bytes, 0897. This tells the computer, hey, this 08 that you have right here, it's not from the ASCII code table. It says we're going to have 8 of something. Okay, what are we going to have 8 of? Character 97 from the ASCII code table, which is lowercase a. 255, this tells the computer, hey, this 10 has nothing to do with the ASCII code table. It means we're going to have 10 98s. What is 98 on the ASCII code table? That is the letter B. So now we move into this CD, CD, CD. Notice right here with the 99, which corresponds to the letter C, there is no flag. And it says right here, if there is no flag, that very next byte, the 99, is taken with the preceding 0, 1. So the computer understands we do not see the flag. We're looking for character 99, which is C. The 100, we don't see a 255. It's not repeating. We're simply going to output 100, which is the letter D, and then it repeats C, D, C, D. Then we get to our flag where a bunch of E's are repeating. 255 tells the computer, okay, this 8 has nothing to do with the ASCII code table, because remember, the flag shows there are repeating values that deal with the next 2 bytes. So we have the flag. Our first byte is the quantity of the characters we want, which is 8. The second byte deals with the ASCII code character, which is 101. So now lossless compression has now reduced the file size to 15 bytes. We started with 32 bytes, but now we've reduced it to 15 bytes. And what's important is because it's lossless compression, we have kept all the data, but we have saved 53% storage space, which is actually, when you do this over lots and lots of files, you actually can store a lot more than you think you can because of lossless compression. All right, let's move on. Let's talk about compressing an image using run length encoding. Now, you can compress an image using lossless compression by employing run length encoding. Now, run length encoding is lossless compression. It's a form of lossless compression. You would only do this if it would be beneficial to use lossless compression over Lossy. Now, in this example, white is represented by a binary value of 1, black is represented by 0, and we have the character F here. So if you look, you can see in this top row, we have all 1s, then we have a white, followed by black, followed by another white, and that's what the second row shows. 1, 0, 0, 0, 0, 0, 0. and then 1. And then you can see here, these next 2 rows repeat because we only have these shaded in. Now, when you look at the compressed RLE format, it can be a little confusing, but it isn't really. Having to write all this out can be very long. I make my students do this on a sheet of graph paper to understand how long it takes and how hard it is to read, because you can easily lose your place, especially if it's not the letter F, if it's an image that we can't tell. Now for RLE format, we have 9W. What do you think that means? 9 whites, 6 blacks, 2 whites, 1 black, 7 whites, 1 black, and so on. And what we do here is we use 9-1. What does 1 refer to? 1 refers to white. We have 9 whites followed by 6 blacks. Now, if you're looking over here, you'll see there's 1, 2, 3, 4, 5, 6, 7, 8. You may be saying, well, hold on here. There's 8 whites, not 9. But it's not about just building 1 row at a time. How many whites do I have in a row? It says 9 whites followed by 6 black followed by 2 whites. So let's do that. Let's see if we get 9 whites. 1, 2, 3, 4, 5, 6, 7, 8. Now that row is done, you move to the next row, 9. That is where the 9 white is coming in, followed by 6 black. So we have, as soon as I get my mouse, 1, 2, 3, 4, 5, 6, followed by 2 whites. 1, done with this row, I go to the next and I continue my count. 2 whites, 1 black, 7 whites. 1, 2, 3, 4, 5, 6. Done with this row, and I go to 7. So when you're looking at the RLE format over here, you may be saying they made an error. No, they didn't. It's 9 whites in a row, and when you finish with 1 row, you immediately go to the next row. Okay, so let's talk about lossy compression for an image file. So these are 2 identical images, I should say. In an image file, you may not need the highest resolution. Now, the file is going to be close to the original, but it will take up less space by using lossy compression. Now, once the file is converted to JPEG, the JPEG will never be able to be converted back to the raw file, and that's because information has been lost in lossy compression. For example, the raw image, you can see in the sky, there are multiple colors here. When you're looking at the JPEG, some of that detail has been lost, but it's still an acceptable picture. Looking at this couch, you can see some, deep, darker colors than you can over here in the JPEG. This rug over here looks a lot different in the JPEG than it does the raw file, but we can still tell that there are buildings in the background. We have a couch, we have a rug, we have a table. We just have lost some of the detail because we don't need all the detail. So, and this is just citing my sources from picturecorrect.com. All right, vector graphics. They're defined in XML text files, which allows them to become compressed. Now, because it's a text file, we can say it is lossless, although most of the time vector graphics can be adjusted without losing quality. We talked about this with bitmap images. Bitmap images, when you stretch them out, they become distorted because the amount of pixels don't change. Vector graphics, we say that it's a text file because it's defined in XML text files, and they're redrawn every time you enlarge them. So we say that would be lossless instead of lossy because you're not losing any of that data. All right, lossy compression for an audio file. Now, MP3 uses audio compression to convert sounds to MP3. This reduces the file size of a normal music file by about 90%. Now, in our Volbeat example, we saved right around 86%, which is still close to 90. Streaming MP3s will be much better than streaming the original file. Think about how long it would take to load 45 megabytes or, God forbid you're on a data cap. If you're streaming an album, you're going to be streaming gigs of music rather than megabytes of music or data. So you definitely want to use MP3s. Now, MP3 music quality will never match the sound file on an original CD, but it's satisfactory for most purposes. And this is done by what is known as perceptual music shaping. So here's what happens when they make an MP3. In perceptual music shaping, the frequencies that are outside the human hearing range, we simply remove them. So if there's some sounds that we cannot hear, they just take it out. Well, when you're taking information out, that is going to reduce the file size. If 2 sounds are played at the same time, but only the latter one can be heard by a human, they're going to take the other one out because it can't be heard. When you're taking information out, it's going to be reducing the file size. Now, it's important to note that bitrate can increase the quality or decrease the quality of an MP3. For example, a 56 kilobits per second quality versus 320, you're going to have a noticeable difference. And we're going to take a look at that in class with an exercise. I've had a few students say that they're able to tell the difference between 320 and 128, and that's what a standard MP3 is 128, usually tops around 320. I've had several students say, oh, I can tell the difference, and out of all the students who have come through my class, only 2 have been able to do it at the time of this recording. So let's take a look at a graph to see how we actually lose sound for an audio file. So, for example, this was our original audio file, this red line, and say we want to take it down to 2 bits. Well, notice the sharp increase here. I don't have this gradual increase. My blue line is what I have to use. And you can see the sudden decreases here based on the bit information, the digital information. I lose this gradual upswing. I lose this gradual downplay. Like right here, it just suddenly drops. And then it goes over here, the pitch suddenly drops. And right here, it suddenly drops. So we're losing all that information just by doing 2 bits. Now, let's talk about general compression overall. There are some general methods of compression without needing lossy or lossless compression. For movie compression, for example, we don't use lossless or lossy. We're going to use movies, and here's how we do it. They reduce the sampling rate, they reduce the sampling resolution, and they reduce the frame rate. By taking data out, you are lowering the size of the movie. For an image files, well, we crop images, we decrease the color bit or depth, and we decrease the image resolution, so we still get an acceptable quality picture, but it's not the same. Now, once you compress a movie into the image files, you're not going to get the original back. If you, for example, there are DVDs. DVDs are compressed sound and video. When you get a Blu-ray, that is uncompressed video and uncompressed sound. And that's why Blu-ray is considered better than DVD. Blu-rays are uncompressed. DVDs are nicer than VHS, but they're still compressed. Now, what about colored images? Well, run length encoding can help with colored images, and we'll be doing that in class. So that completes your podcast. Make sure you bring your notes, because we're going to be using all this information on our homework, Cambridge questions. We're going to be doing colored images. So get ready. It's going to be an interesting class. If you guys, for those of you not in my class, if you have any questions, please post a comment below. We'll see you guys in the next video.